Hello and welcome. Last time we did proportional only control of the temperature in a simple heated surge tank. This time what we will be looking at is proportional integral temperature control of the surge tank, where the integral time has been taken to be the same as the tank residence time. For this system, the base case conditions are as before shown here, and what we are doing is temperature control. We are controlling the temperature of the tank by adjusting the heating duty, and this controller is a PI controller. For this situation, the process dynamic model that was derived last time was this, and now because the controller equation is that of a PI controller, what we have is where this is the bias term. The time constant and the process gain are as here for the base case conditions shown. So here's the controller equation. So if I could put this over here, what I get is tau dt over dt plus t is equal to t naught plus k times q steady state plus kc times t set point minus t plus 1 by tau I integral of t set point minus t dt. We know from the initial steady state balance that k times q is actually t minus t naught. So substitute this over there and take the t bar term to the left hand side and keep the t naught bar term on the right hand side. Then what we get is tau dt hat by dt plus t hat is equal to t naught hat, where the hat denotes deviation from the initial steady state value, plus kkc into add and subtract t bar. So you will have t set point subtract t bar minus add, sorry, for addition you'll have to have a sign minus here, minus t bar plus 1 by tau I into integral of add and subtract. So subtract t bar, add t bar. And so what this gives is, this is the t set point deviation, and that's again t deviation, t set point deviation, t deviation. So what we get in terms of deviation variables then is tau dt hat by dt plus t hat is equal to t naught hat plus kc into t set point hat minus t hat plus 1 by tau I into integral t set point hat minus t hat dt. So this is the governing differential equation in terms of the deviation variables. T naught is a disturbance, t set point is for the servo change. I can further, now to remove this integral sign we'll have to differentiate both sides, but before we do that let me simplify a little bit further. So we'll have tau dt by dt plus t tilde is equal to t naught plus kc divided by tau I, and what I'll do is differentiate both sides. See, if I differentiate both sides, this is what I'll get, and of course I'll get d by dt and then I'll get the differential of the integral is going to be the function itself, so the differential and the integral will cancel each other, and so what you will get here is tau I times dt set point by dt plus t set point, that's one term, minus tau I times d by dt of temperature deviation plus the temperature deviation. This is what you get. Now if you put tau I is equal to tau, some simplifications will happen, and I'll do those simplifications shortly. So please bear with the slight delay as we get a clean slate to write on. Well, the slate is clean enough. Now we put tau I is equal to tau. This tau I is again equal to tau, and then what you get is in operator form, where d by dt is an operator, so we get d by dt and tau d by dt plus 1. This operates on the function t tilde, should be equal to d by dt operating on t naught tilde plus kc by tau I times the operator tau d by dt plus 1 operating on t set point tilde minus kc by tau I, and tau I is equal to tau, by the way. This is equal to tau. So we are taking the case where tau I is set equal to tau, times tau d by dt plus 1 operating on t tilde. Take this term to the left hand side. Take it to the left hand side. And if you take it to the left hand side, then what we get is you will have tau d by dt plus 1 common. So take that operator as common. Tau d by dt plus 1 is common. And then you get d by dt plus kc by tau operating on t tilde is going to be equal to d by dt operating on t naught tilde plus kc divided by tau times the operator tau d by dt plus 1 operating on t tilde set point. Now this, if t naught changes, we get the regulator response. If t set point changes, we get the servo response. That's the servo regulator, and this one is servo. Okay, now let us say we are looking at the servo response. If you are looking at the servo response, that means t naught tilde is 0. So for the servo response, this term will go to 0, and then you are left with what you are left with, and you can see that these two terms are common. Because these two terms are common, they cancel out, And then what you get is, for the servo response, you have d by dt of t plus k kc by tau times t tilde is equal to k kc by tau into t tilde set point, multiply by, make the coefficient of t tilde 1, and so what that gives is d tau by kkc into d t tilde by dt plus t tilde is equal to t tilde set point. So this is the governing equation. This is the governing equation for the servo response. It's a first order equation with time constant as here, gain is 1, and we've solved this kind of an equation before, and we know that the solution of this is for a step change in t set point where t tilde set point is equal to delta t set point. That means set point is somewhere, and then you give it a step of size delta t set point. Okay, so this is the t set point signal. So if t set point is changed like this, then we know that t tilde, if we use the integrating factor approach, is going to be 1 minus e to the power minus t by tau prime, where tau prime is equal to tau by kkc times delta t set point. So this is the servo response. If you want the regulator response, then this neat cancellation that happened previously does not happen, and you actually end up getting a second order differential equation that must be solved. And let me just derive that equation, and then we'll try and solve it quickly, as quickly as we can. So for the regulator response, what we have is, if you want the regulator response, then t set point deviation is set equal to 0, and therefore this term goes to 0. Because this term goes to 0, what you get is tau second derivative is equal to d by dt of t naught minus k kc by tau into tau d by dt of t tilde plus t tilde. This is what we get. Take this term to the LHS. If you take it to the LHS, then what we get is tau second derivative one plus yeah plus kc by tau into t tilde, that's equal to dt naught tilde by dt. Now in order to solve this equation, let's first put it in standard form. Standard form, what you do is you make the coefficient of the t term 1. In order to do so, you multiply both sides of the equation by tau by kkc. If you do that and do some of the algebra, which I'll do right now, you'll get an equation with which to work. So multiply by tau by kkc both sides, and what then you get is tau square by kkc into second derivative plus tau by kkc into 1 plus kkc plus t tilde is equal to tau by kkc into derivative of. This is the governing equation. Note that in this governing equation, the right hand side, the forcing function, is not a unit step, but the derivative of a unit step, which will be a Dirac delta of area A of area 1. We know how to solve. Now in order to solve this, the approach that we'll take is assume forcing function is a step. RHS is a step. In reality, it's going to be derivative of that step, but assume it is a step. Solve this equation for that step forcing. So if the input is step and the governing equation is the left hand side of the equation of the ordinary differential equation, and let us say you get some kind of a response, let's say the response is something like this, then if you take the derivative of this step, which is if you take the derivative of the input, if you take d by dt of this, then the output is going to be d by dt of the output. So the approach we are going to take is solve this equation assuming a step forcing, and then whatever is the response that we get, tau by kkc times derivative of that response will give us the actual response to this derivative forcing. I hope this is clear to you. So this is what we are to do. Now how do we solve a ordinary differential equation of second order? See, I hope you have done this in MO1, MO2 or one of those mathematics courses, but the basic idea is, see, if you look at the form of this equation is you take the derivative, second derivative plus something times first derivative, and So if there was no forcing, that is the homogeneous ordinary differential equation where there is no forcing and the right hand side is 0. For a no forcing kind of situation, what we are looking for is that function of time which when differentiated twice and once gives the same function, and we know this property is of the function e to the power lambda t. Differentiate it n number of times and you will recover the same function, and if you are differentiating it twice, maybe you will get lambda square. If you are differentiating it n times, you will get lambda to the power n times e to the power lambda. So you recover the function with a multiplier. So this property of recovering the function after differentiation is that of e to the power lambda t. So the way to solve this equation, integrating factor will be difficult because integrating factor applies to a single first order differential equation. So the general way of solving this equation is to use the method of constant coefficients. And what is the method of constant coefficients? You say, okay, the total solution, we are looking for t. So t tilde total is going to be t tilde complementary plus t tilde particular. T complementary satisfies homogeneous equation. Homogeneous, and what we mean by homogeneous is unforced. Homogeneous ODE. Homogeneous means unforced. That means RHS is 0, no forcing. And TP is a particular solution that satisfies the forced ODE forced ODE. And note that TP will have the same form as the forcing function because left hand side must be equal to right hand side. So TP has same form as forcing function. So the complementary part of the solution that satisfies the homogeneous ODE, it must have the form TC must be of the form sum of, well, TC must be of the form some constant times e to the power lambda t. It must be of this form. So if I substitute c e to the power lambda t into the homogeneous part of the equation, then what I get is tau square by kkc into lambda square times c e to the power lambda t plus tau by kkc into 1 plus kkc times c times lambda times e to the power lambda t plus c times e to the power lambda t. This must be equal to 0. This is called the characteristic equation. This and the c cancel out, and then what you get is the characteristic equation. The usual form of writing the characteristic equation is to make the coefficient of the highest power of lambda 1. So the characteristic equation, after you've done the necessary manipulation, is going to be 1 plus kkc by tau lambda plus kkc by lambda square is equal to 0. This is the characteristic equation of the ordinary differential equation that describes the system response. This characteristic equation is of order 2. It's a polynomial in lambda of order 2, so it will have two roots. What are those two roots? So lambda will be equal to minus 1 plus kkc divided by 2 tau plus minus square root 1 plus kkc whole square minus भैया ये टाउ स्क्वायर है सॉरी माइनस kkc divided by 2 tau. There will be a 4 here, so that's going to be equal to minus 1 plus kkc divided by 2 tau plus minus kc minus 1 divided by 2 tau, which gives lambda is equal to minus 1 by tau, and the other guy will be minus kkc by tau. So these are the roots that satisfy the characteristic equation. Both these roots are negative, and so T complementary or the solution of the homogeneous part of the ordinary differential equation is going to be C1 e to the power minus t by tau plus C2 e to the power minus kkc by tau times t. This is going to be, you see, if e to the power lambda 1t satisfies the ordinary differential equation and e to the power lambda 2t satisfies the homogeneous part of the ordinary differential equation, then a linear combination of these two also satisfies the ordinary differential equation. So in the general form of the complementary part of the solution is a linear combination of the exponentials corresponding to the special values of lambda that come from the homogeneous part of the ordinary differential equation. T particular will have the same form as the forcing function, and we are going to take the forcing function is a unit step. Eventually it's going to be a differential of the unit step, but first we are going to solve for the unit step. So T particular for a unit step forcing is going to be a constant C0. This T particular must satisfy the forced ordinary differential equation. That means it must satisfy this entire equation, and if I substitute C0 for t tilde into this equation, second derivative of constant is 0, first derivative of constant is 0, t tilde is C0. So what you get is C0 must be equal to, forcing is a unit step, so right hand side is okay, the right hand side is RHS is equal to 1. Okay, so right hand side is equal to 1, so C0 must be equal to 1. So the total solution T total is going to be 1 plus C1 e to the power minus t by tau plus C2 e to the power minus t by tau. How do we get the C1 and C2? This C1 and C2 we get from the initial condition. What are the initial conditions? The initial conditions are at time t equal to 0, just before forcing the step, t tilde is equal to 0. Also the system is at rest, therefore at time t equal to 0, derivative of t tilde, time derivative of t tilde is 0. So your initial conditions are t tilde total is equal to 0 at t equal to 0, and d by dt of t tilde total at time t equal to 0 is equal to 0. These are the two initial conditions. If I apply these two initial conditions, what I get is, from the first initial condition at t equal to 0, this term, the exponential goes to 1, both the exponentials, by the way this is t prime, where tau prime is equal to kc by tau. Okay, so what you get is, from the first initial condition you get c1 plus c2 is equal to minus 1. From the second initial condition, what you get is c1 plus kc c2 is equal to 0. c1 plus c2 is equal to minus 1, and c1 plus kkc into c2 is equal to 0, and therefore what you get is, if you subtract these two equations, what you get is c2 is equal to 1 over kkc minus 1, and c1 will be minus kkc over kkc minus 1. Just confirm, c1 plus c2 should be giving minus 1, so c1 plus c2 is, yeah, so this is fine. So what this gives is, if the forcing function was a unit step, then t would be 1 for a unit step, 1 minus kkc upon kkc minus 1 e to the power minus t by tau plus 1 over kkc minus 1 into e to the power minus t by tau prime, where tau prime is this chap. This is for a unit forcing, but if I am doing tau by kkc times derivative, then the actual response is going to be, t tilde actual is going to be tau by kkc multiplied by derivative of the right hand side of this equation. Let me call this equation A. Derivative of the right hand side of the equation A. And if you do that, maybe we should spend some time doing that. What you then get is t tilde is equal to tau by kc, derivative of this chap is going to be, derivative 1 is 0, derivative of this is going to be minus kkc divided by kkc minus 1 times e to the power minus t by tau, माइनस माइनस पॉजिटिव हो जाएगा, डिवाइडेड बाय टाउ. उधर क्या आएगा, उधर आएगा माइनस टाउ प्राइम इज के के सी बाय टाउ. ओके, सो दिस इज गोइंग टू बी माइनस के के सी बाय टाउ टाइम्स के सी minus 1 e to the power minus t by tau prime. And so when you multiply by tau, this tau and these two taus cancel out. So what you get is t tilde is equal to, in fact the kkc also cancels out. It's a very nice expression. 1 over kkc minus 1 times e to the power minus t by tau minus e to the power minus t by tau prime. So this is the final expression that we get for the variation in temperature with time. Alright, so let me just summarize how we derived this, and that summary is going to be quick. So the case is tau I is equal to tau. If we substitute, differentiate and rearrange, this is what we get. And in operator form, this is what this is. For a servo response, if you put this equal to 0, we'll have these two terms cancelling out, and because these two terms cancel out, what we get is this as the governing differential equation. And for this, the servo response expression is as shown in magenta. For the regulator response, for the regulator response, t set point has been set to 0, and this is what you get. So when you take this guy to the left hand side, the differential equation solves to this, and this differential equation is a second order ordinary differential equation, and we are going to use the method of constant coefficients to solve it. So here's the differential equation. The homogeneous part is, put the right hand side equal to 0. The homogeneous part is satisfied by this equation, and if you substitute this into the homogeneous equation, you get the characteristic equation. This must be satisfied, and the solution for this, these are the two roots of this equation, and therefore the homogeneous part of the solution will look like this. We assume that the forcing function is a unit step and not the derivative of a unit step times tau by kkc. So for a unit step forcing function, particular solution must satisfy the unit step forced ODE, and if you substitute, so the particular solution must be a constant because the forcing function is a constant, and if you substitute this into the differential equation with the right hand side equal to 1, if you substitute this into the ODE with the right hand side equal to 1, what you get then is this constant is equal to 1. So therefore the total solution is going to be of this kind. Initial conditions are deviation in the temperature is 0 at time t equal to 0. This gives C1 plus C2 is equal to minus 1. Derivative of the temperature at time t equal to 0 is 0. This gives C1 plus kkc C2 is equal to 0. And if you solve these simultaneously, you get C1 as shown here and C2 as shown here. And therefore the solution is as shown here, and this is correct. Now this is the solution to unit step forcing. the actual forcing is derivative of the delta T naught step. So actual forcing function is tau by kkc times derivative of the delta T naught step, and therefore the actual solution must be tau by kkc times derivative of the solution for the delta T naught step, where delta T naught is a step. And when you do this, the final regulator step response turns out to be this. This is what I had derived. And of course, what I derived was for a unit step. If the step size is delta T naught, because it's a linear system, the response will be delta T naught times the unit step response. So this is what we have derived. This is a summary of what we derived. I simulated regulator response and servo response. By the way, this is Q percent. So just make a note of this. So if delta T naught is increased by 1 degree Celsius, you remember the change in temperature the outlet temperature used to go from 60 to 61. If you remember, when we did no control, this response was something like this, and it will go to, the change in temperature would be 1 degree Celsius. With control, what we are getting is, and I'm using different values of kkc, kkc is increasing. You can see whether you use small kkc or large kkc, because tau I is equal to tau, you are using integral action. Ultimately, the temperature returns back to set point. If kkc is increased, the return to set point is faster, the response completion time is faster, quicker, and the change in the Q is more aggressive. If you look at the servo response, again you'll see as kkc is increased, the response is faster, quicker, there is no offset, and as kkc is increased, the change in the change in Q is more aggressive, larger and more aggressive. So what this small exercise has shown is that the temperature response is smooth, there are no oscillations, the response speed increases as the controller gain is increased, the aggression in the change in Q increases as the controller is made more aggressive, as Kc is increased, and most importantly, if the set point remains constant, then regulator response and servo response, eventually there is no offset, the temperature ends up at the set point. As an exercise, oh shucks, what did I do? I made a mistake, so well, let's correct the mistake. So we'll correct the mistake. As an exercise, see, the tank is a lag. The tank is a lag in the sense that tau dt by dt plus t is equal to k times q. That's a lag, first order lag. But any realistic system, you've got a valve. The valve will have its own dynamics. You've also got a sensor. Sensor would be a thermometer. So the thermometer, if the fluid temperature changes, the thermometer temperature will not change immediately. If the fluid temperature changes, the thermometer will take some time until the thermal equilibrium is attained. See, that is why when you measure your temperature, you put the thermometer into your mouth and wait for 1.5 to 2 minutes. So it takes 1.5 to 2 minutes for the thermometer to equilibrate with the fluid temperature, with the body temperature. Yeah, so there is the measurement. So this is the actual fluid temperature and this is the measured temperature from the thermometer. So there is a dynamics associated with the sensor, and you also have dynamics associated with the heating circuit. You change the valve position and more steam starts coming in, the pipes get hotter, and as the pipe gets hotter, heat gets transferred, more heat gets transferred to the fluid in the tank. So if this signal goes up, again, for the Q to, it takes time for Q to reach the desired controller demanded value, and therefore this is the Q coming from the controller and this is the Q that is actually delivered to the fluid. So there are heater dynamics and there are sensor dynamics, and so what I'm saying is that obtain the dynamic response of T measured to a step change in T naught or QC. That means the signal to the valve is changed, or T naught changes, signal to the valve changes as a step, or in your process T naught changes as a step. Yeah, but then there are sensor dynamics. There's an ordinary differential equation relating the sensor dynamics, and there's another ordinary differential equation relating the heater dynamics to the demanded controller Q. Okay, and I'm just saying that tau s and tau h are 0.5 and 2 minutes respectively. This is a more realistic system. Obtain the ODE relating Tm to T naught and QC. Obtain the dynamic response of Tm to a step change in T naught or QC, and do this for a P controller. Let's not do this for a P controller only. So this is the exercise that you're supposed to do. Please do it immediately after watching this lecture or as quickly as possible, and you will see that for a P controller with 3 lags you will have a third order characteristic equation, and there are going to be 3 roots, and depending on what Kc is, okay, so we are not going to do control here, leave that for the time being. So if T naught changes, it's a third order system. If T naught changes or if QC changes, what is the response of Tm? So this is just an open loop response, no control. Okay, so this is the exercise that I'm asking you to do. Please do it as soon as you watched this video. In summary, we have looked at PI controlled system dynamics for the simple surge tank, heated surge tank. The dynamics are described by a simple ordinary differential equation with parameters depending on operating conditions and the controller tuning parameters. The servo response is an ODE. The servo response is described by an ODE that is first order for tau I is equal to tau, and this first order thing comes because of cancellation of d by dt plus 1 term. Regulator response is a second order ODE which was solved using the method of constant coefficients. In all cases the response is smooth, that's smooth exponential that speeds up as Kc is increased. The integral action removes offset from the constant set point, and eventually finally the temperature ends up at set point. The method of constant coefficients, a brief summary of this is as follows. The solution of an ordinary differential equation with constant coefficients is given by the sum of the particular solution and the homogeneous solution. The homogeneous solution satisfies the ordinary differential equation with no forcing. The particular solution satisfies the forced ordinary differential equation and has the same functional form as the forcing function. So the homogeneous solution satisfies the unforced ODE. It is a linear combination of exponentials, and these exponentials are obtained by substituting or obtained from the characteristic equation. The lambdas are obtained from the characteristic equation. which ends up being a polynomial. So if it's a third order ordinary differential equation, your characteristic equation will be of order a polynomial of order 3, and so it will have 3 roots. Particular solution satisfies the forced ODE and has the same form as the forcing function. For example, y particular is equal to a constant for a step forcing function. And that's that. So with this we come to the end of this lecture, where we have seen slightly complicated dynamics due to control. I hope you enjoyed the lecture, and I hope to see you next time. Thank you very much for your kind attention. Goodbye. See you next time. Thanks again.